which was for 30 degrees, will reflect OP8 about the x-axis, so we have a segment creating a negative 30 degree angle from the negative x-axis. Now the central angle is 60 degrees with two sides of length 1. Therefore, we now have an isosceles triangle, meaning the base angles must be congruent. Since the interior angles of a triangle add up to 180 degrees, the base angles must be 180 minus 60 divided by 2, 60 degrees each. So we have our equilateral triangle again, giving us the length of 1 for the third side, the chord. Since segment OP8 is 30 degrees above the negative x-axis and its reflection is 30 degrees below the x-axis, and since both segments have endpoints at the origin and on the unit circle, then the negative x-axis bisects the chord. Therefore, point P8 is 1/2 of a unit from the negative x-axis, meaning sine of 150 degrees equals 1/2. Recall that sine of 30 degrees also equaled 1/2, and also recall that 150 degrees equals 180 degrees minus 30 degrees. We will calculate cosine of 150 degrees using the distance formula that we used in calculating cosine of 30 degrees. Since we already know the distance from the origin to P8 is 1, which is the radius, and the sine of 150 degrees is 1/2, then after the calculation and plugging things in, we get plus or minus cosine of 150 degrees equals plus or minus square root of 3 over 2. Since cosine of 150 degrees is the x-coordinate of a point in the fourth quadrant, its value must be negative. Therefore, cosine of 150 degrees equals negative square root of 3 divided by 2, which equals negative cosine of 30 degrees. Looking back on the 150 degree problem, the x-axis bisects the chord from point P8 to its reflection, meaning sine of 180 minus 30, which is the sine of 150, equals 1/2, which equals negative sine of 210 degrees. Using the distance formula from the origin again, we see that plus or minus cosine of 210 degrees equals plus or minus square root of 3 divided by 2. Since cosine of 210 degrees is the x-coordinate of a point in the third quadrant, it must be negative. Therefore, cosine of 210 degrees equals negative square root of 3 divided by 2, which is also equal to cosine of 150 degrees. This sets us up perfectly to see that sine of 180 degrees minus theta equals the negative of sine of 180 degrees plus theta, and cosine of 180 degrees minus theta equals cosine of 180 degrees plus theta. More generally, reflecting the angles over the x-axis keeps the same values for cosine, but switches the signs for sine. Looking at the picture below, it's easy to see why. The tangent function is the slope of the radius, therefore it's the rise over run. For an angle, the rise is the sine and the run is the cosine. Therefore, tangent of theta equals sine theta divided by cosine theta. By taking the sine and cosine values from the previous table, we get these values for tangent. So what if the unit circle had a radius of 2? Basically, what if we weren't dealing with the unit circle anymore? Then we find the same ratios would still hold. By dropping a perpendicular from line AC at the midpoint and a second line at line CE, we find that triangles ADB and AEC are similar. They both have the right angles, and they share an angle at A. Since they have two of the same angle measurements, and every triangle has interior angles that add up to 180, the third must be the same also. So because of the similarity, they will have congruent ratios of corresponding sides. Since line AB is 1/2 of AC, and we're saying here that AC is 2, AB is 1, part of the unit circle. So line BD is the sine of theta. So the sine of theta divided by CE equals 1/2. Line CE equals 2 sine of theta. SOHCAHTOA. Sine, cosine, and tangent can also be defined using right triangles. Sine of theta equals the opposite over the hypotenuse. Cosine of theta equals the adjacent over the hypotenuse. And tangent equals the opposite over the adjacent. Are the unit circle definitions of sine and cosine equivalent to the ones using right triangles, SOHCAHTOA? Let's remember how we defined using the unit circle. Sine theta is the y-coordinate of P, a point on the unit circle such that theta is the angle between line OP and the positive x-axis. Cosine theta is the x-coordinate of P, a point on the unit circle such that theta is the angle between line OP and the positive x-axis. Tangent theta is the slope of the radius, the rise being the sine and the run being the cosine. Using SOHCAHTOA, when the hypotenuse is 1, which happens when we use the unit circle, gives us sine theta equals the opposite, and cosine theta equals the adjacent. As you can see in the picture of the right triangle, the opposite is the height, or the y-coordinate of the top point, which would be on the unit circle, and the adjacent is the x-coordinate. But what if the hypotenuse wasn't equal to 1? Recall how we proved that we had similar triangles when two triangles shared the same theta angle, one on the hypotenuse equaling 1 and the other with the hypotenuse not equaling 1. Since they were similar triangles, their corresponding sides were proportional to each other. That's why the unit circle definition for sine and cosine turn out to be an equivalent to the SOHCAHTOA definitions no matter how long the hypotenuse is. As for tangent, earlier we defined it as the slope of the radius, meaning tangent equals sine over cosine. By substituting the SOHCAHTOA sine and cosine definitions in, we get tangent of theta equals opposite over adjacent. That's why the unit circle definition for tangent turns out to be equivalent to the SOHCAHTOA definition of tangent no matter how long the hypotenuse is. How about a derivative? To find a derivative, first we need to find the limit of sine theta divided by theta. Draw a unit circle with an angle and drop a perpendicular. This angle theta times the radius of the circle, which in this case will be 1, will be an arc length of the angle. So as the angle decreases, the arc length has less curvature and the sine of theta gets closer to the point 1, 0. So the difference of length becomes less as the curvature is decreasing. So the limit as theta goes to 0 of sine x divided by x equals 1. How about a second derivative? By using the definition of a derivative and the trig identity, we can simplify to the derivative of sine x equal to cosine x. To see this, reference the work to the right. Cosine's derivative. By using substitution and sine's derivative, we can determine the derivative of sine. To see this, reference the work above. Tangent. With sine and cosine's derivative found, we can express tangent as sine divided by cosine and use the quotient rule to find its derivative to be 1 over cosine squared x.